Hello. So this is a video for compiler design, COM 442 and 6421. This is for week 4. This is where I'm explaining in more details what is first and follow sets, which I had introduced in the previous video, but we're not going to go in more details here. I'm going to also introduce again in more detail the predictive parsing methods that I want you to use in the project. So that's going to be both going to more details, explaining the recursive descent predictive parsing, and then introducing how to generate the table and do the parsing with a table-driven predictive parser. Okay. So first, we're going to introduce in detail what is the notion of the first set and the follow sets, as well as their definition, and give an example or formal definition, and then give an example of how to build first and follow sets for our toy grammar. So what is a first set? So the first set is essentially when you have a derivation step, which is transforming, or a series of derivation steps that transform a sentential form alpha into another sentential form beta in many steps. If beta actually starts with the terminal symbol x, then x is in the first of alpha. So essentially you transform the symbols in alpha using the rules in the grammar, and then once you do any number of transformations, all the transformations that are possible, then anything that starts any of the betas that you can generate is it starts with anything that any beta starts with is in the first of alpha. Now, one of the things is, well, that's the general notion of what is the first set, but what we are really interested in is the first of a terminal, a non-terminal symbol, sorry, or a symbol, sorry. We're interested in the first of a symbol, either a terminal or a non-terminal. Well, here you have two rules that actually defines what is the first of a symbol. If it is a terminal symbol, then it cannot be transformed into anything else. So essentially, the first of a terminal symbol is the symbol itself. So if A is a terminal symbol, or A is epsilon, then this A is actually included in the first of A. So that's a trivial case. Then a little bit less trivial, though it's not very complicated, as we see, as we'll see later, follow is substantially more complicated than first. So to compute follow, you actually need first. So second case is, well, there's three cases of the second case. So if the symbol in question is a non-terminal symbol, and you have a rule of this form, okay, and these and this S1 to SK is essentially a sentential form, okay, as we saw in the definition of what is a grammar rule. So if we have this, essentially that we have A is a non-terminal symbol, and we have some rules that define it, which we should. Then the first of A contains first of S1 minus epsilon, because the only case we want for epsilon to be as part of a first set is either that A itself is epsilon, or in the third rule here that we will see later. Essentially, if you have you're trying to define first of A, and then you have a rule that says A can be transformed into S1 something, then of course, whatever can start an S1 also can start an A. So that's what this first rule here says. Second one is if you have any of these S's or any of these S's in the sentential form that defines A, if some of them in sequence can actually evaluate to epsilon, then the first of A contains the first of the next one in the list. So for example, if S1 would possibly evaluate to epsilon given one of the rules defining S1, then S1 can essentially not be there. So essentially it's saying if you're finding first of A and S1 can be null, then first of A contains first of S2, and then so on and so forth in the list. So if S1 and S2 can be null or nullified or epsilon, then S3 would actually be, the first of S3 would be contained in the first of A. And then you go like this over all the list or throughout the sentential form that defines this A for every rule of A. And the last case is essentially if, for example, you have S1 to SK, and they all actually evaluate or can be substituted by epsilon, then essentially it comes to say that you would have a rule A gives epsilon in this specific case. So if you have this, where any of the things or all of the things in the rule and the right-hand side of this rule can all evaluate to epsilon, then epsilon is an element of first of A. Okay. Another thing, well, this is the formal definition. You could also, if you want to generate the first set for a certain grammar or a certain symbol in a grammar, then you may also compute what is called a look-ahead tree for A. So let's go with this example, or maybe let's go with the look-ahead tree. What's a look-ahead tree? So essentially you build a tree that is representing all the possible substitutions that you may have. So for example, if you have E, then given this rule, you can transform E to ET prime, TE prime, sorry. Then if you want to transform this, then you can transform T into FT prime, and then the E prime. And then if you want to transform this, then you can transform the F into any of these three here. And then you have at the leaves of the tree, you have all terminal symbols, which tells you that first of E is actually 0, 1, open parenthesis. Then you can do the same thing with, for example, E prime. So E prime is either epsilon, which is then a leaf of the tree. And as we saw, first of epsilon is epsilon. And then you can also have plus TE prime, which starts with a terminal symbol, thus cannot be substituted. Thus E prime, first of E prime is epsilon plus. So T can be transformed into FT prime. FT prime or F can be transformed into any of these three here. So basically that means first of T is 0, 1, open parenthesis. T prime, much similar to E prime, is either epsilon or star FT prime. None of the symbols here that are first in the sentential form that define it can actually be substituted. So T prime is epsilon and star. And of course, first of F is any of these three here. And then they all begin, all the sentential forms here on the right-hand side, all begin with the terminal symbol, cannot be substituted. So this, the first of F is 0, 1, open parenthesis. Of course, here, this is a very simple grammar. The more the grammar becomes bigger, the more you have alternatives, the more the trees would grow larger and larger. So it's a good way to, graphically see what's the concept of a first set but the real way that you would actually create a program to automatically generate first sets would be using this definition that we saw here. So let's see this more graphically, what's actually happening when you compute the first set using this formal definition. So first we compute first of E. So first of E, if we take this rule here, so that's the first rule, and that's the only rule, but that's still the first one. So we would have to do this for every of the rules that actually define E. In this case, there's only one. So we select this rule here, and then we actually see that this step, or this is not a terminal, what's on the right-hand side here is not a terminal symbol. So it's a non-terminal symbol, so we go to step 1 here. And then it says that essentially first of E contains first of T. That means if we want to compute first of E, we need to compute first of T. Then we go and compute first of T. Then we find that T is defined with only one rule, which is this one here. So we use this rule here. We see that in the right-hand side here, it starts with a non-terminal symbol. So we start with using this rule here. And then we find that it tells us that first of T includes first of F, because what we have here is a non-terminal symbol. So we must expand it to try to determine what can be starting in F. Then, because we don't have first of F yet, then we compute first of F. So eventually we realize that that F can actually be defined by 3 different rules. In the first case, in the right-hand side is 0, which is a terminal. So we use this rule here and infer that first of F contains 0. Same thing goes for all the others, for the 2 others. So we have F gives 1 using this rule here. And then we found this is on the right-hand side is it starts with a terminal symbol. So F contains 1. And then we have F gives E between parentheses. So that starts with parentheses, which is an open parenthesis, which is a terminal symbol. So we find that F contains open parentheses. There are no more rules. And then well, there's only one rule for each of these here. So we basically computed the totality of first of F, okay, which we find is 0, 1, open parenthesis. Then we've computed first of F, and then if we go back to this here, the computation of this here, and if we go to N2, then we realize that F cannot actually be epsilon. Okay, so just step number 2 here actually does not go any further. It does not apply, because none of the symbols in the right-hand side here can start with epsilon in sequence. Even if T prime might evaluate to epsilon, as we see it does here, doesn't matter, because F, that's the first one, cannot evaluate to epsilon. And then, of course, rule number 3 does not apply, because rule number 3 is about what happens if all of the symbols in the sequence evaluate to epsilon. So we found that first of T is 0, 1, open parenthesis. So we have done first of E, first of T, and first of F. In determining first of E, we calculated first of T and first of F. So the only one that's remain is first of E prime and first of T prime. Let's go first of E prime. So for E prime is plus T E prime or epsilon. So let's expand them in order. So we have E prime gives plus T E prime. So what starts the right-hand side here is in the sequence is plus, so it's a terminal symbol. So we use this rule here, and then we say plus is included in E prime. And of course, this was a terminal symbol. That's the only rule that applies. Then we take the second rule, which is this one here. And then we have E prime gives epsilon. And then the only rule that applies is this one here. So we have that first of E prime includes epsilon. And that's all there is to it. So first of E prime contains or is plus an epsilon. Then very similar for first of T prime. So we have T prime is either star FT prime or epsilon. So let's take these two rules in sequence. So first, the sentential form on the right-hand side here starts with star, which is a terminal symbol. So we use this rule here. So that rule tells us that star is actually included in first of T prime. And then of course, that's the only rule that applies. And then we have T prime gives epsilon, and then again, the same rule applies, and that's the only one that applies. So first of T prime contains epsilon. So now we have found that first of T prime is star epsilon. So that's how you use this formal definition here. Now, for the project, I have actually designed a tool that actually implements exactly this procedure here, and that you will be able to use to extract the first sets from the grammar. Okay. Same thing for also the follow sets. There are plenty of tools that you can find on the internet that would allow you, given a certain grammar, that you feed this grammar to the tool and then gives you the first and follow sets. But it's very important that you know the concept of the first and follow sets, because if things go wrong in your parser, if you don't really understand what's this first and follow sets, you're going to have a hard time understanding what's wrong with your parser. Plus, there is going to be exam questions about that in the exam. So let's go to follow sets. Now, as I said, follow sets is substantially more complicated. It's not rocket science anyway, but follow sets is a little bit more complicated and abstract, I might say. So what is conceptually follow set? So follow of A. So again, here we're concerned with follow of a symbol. Okay. In this particular case, we're concerned only with follow of a non-terminal symbol. There's no such thing useful in a parser's operation as follow of a terminal symbol. Okay. So that's why we're only concerned in the definition with follow of a non-terminal. You could compute follow of a terminal, but in the operation of a parser, it's not a concept that is being used. So follow of A is a set of terminals that can come right after an A in any sentential form derivable from the grammar of the language. So essentially, if you have, what's going to happen is that you're going to go forward in parsing each of the symbols in the sentential form on the right-hand side of a rule. Then what you're going to want to know at some point in time is what is it that can, after you have parsed a certain non-terminal symbol, what are the valid possible tokens that you can find after you have finished parsing this particular right-hand side that define this symbol. Okay. So that's why you actually need this notion of the follow set. Again, first and follow sets, you might think, well, we're just only talking about the parsing methods that we're going to see in this lecture. No, first and follow sets is actually pervasive to all of the parsing techniques. Well, I would say the vast majority of them. So what is the formal definition of follow set or follow set of a non-terminal symbol? First of all, if this non-terminal symbol is the starting symbol, then what can follow the starting symbol is the end of the program. So basically what it says is that if you successfully parse a program and you prove that this program is a valid program, there should not be tokens after the end of the program. Okay, that should be what the only thing you should find after the program is the end of the file. That's basically what this rule says. Pretty simple. Then if you have a rule in your set of rules that is the form B gives alpha A beta, then follow of A includes first of beta. So you see that you have this A here. So once you've finished parsing this A, what you can find is what starts beta. And then you remove epsilon, because we don't want to have, or it doesn't make sense to have epsilon in a follow set. So basically you scan all the rules in your grammar and you try to find this pattern here where a sentential form is actually contains the symbol that you are looking for. Okay. Then the rule here says that, well, if you still have the same thing and that beta can actually be nullified, then you actually have found or can infer that follow of A includes follow of B. Because if you finish parsing an A and you find, and this beta here, or actually if A can end the sentential form that defines B, then by inference, you can say that whatever follows a B is also what can follow of A. So you see that it's the same, essentially the same rule, except that here you will find whether all the symbols in beta can actually be nullified, or that actually you have a rule of the form B gives alpha A and then nothing. Basically that A finishes the sentential form, which is the same concept as if beta would be there, but is actually can entirely be nullified. So that is the formal definition of the follow set. So let's see with an example. So again, we have here our rules. We have our first sets, okay? Because this, as you may see, the definition of follow is actually using the first set. So you must compute the first set before the follow set. So this is the first sets that we found in previous example for this grammar. And here we're going to construct the follow sets by using this formal definition of the follow set and the rules in the grammar. So what we are doing here, we're essentially taking every of these rules here. This is essentially some kind of pattern that you're looking for in your grammar, and you're trying to see where does this pattern, what are all the occurrences of every of these patterns in your grammar. Okay. Then you apply, when you find this pattern, you apply the rule that gives you an inference, and you find a certain fact about follow set contains a first set or follow set contains a follow set. So first one is if A is the starting symbol, then follow of A includes the end of the program. So what is A in our grammar? Well, our starting symbol is E. So we have one rule that defines E, which is this one here. So here the inference that we are looking for, the pattern that we're looking for is this one, and then it's the inference that we can use. So if A is equal to S, where A is E, then follow of A include $sign. So follow of E includes $sign. Follow of E includes $sign. So you see here that what we're finding is inclusion relationships. Okay. So this one is okay, because here what I have in this set here is actual terminal symbols. Okay.
So we will see later that when you find, so that's fine with these because these are all known sets. Okay. However, these here, what you have on the right-hand side here, are not necessarily known sets. These are just inclusion relationships between sets. I'll come back to that later. And that's one of the things that is a little bit more complicated in computing the follow set, which I'll again come back to later. Then we're looking for occurrences of the rule number 2 here, okay, where we have B gives alpha a beta. So here I might be looking for using this rule here, using this grammar rule here, using rule number 2 here. Then I can actually find if E gives TE prime, and I'm looking for this pattern here, then I actually can say, well, if alpha is not there, and I say A is my T and beta is E prime, then I can, the inference I can make from that is that follow of A includes first of beta minus epsilon. So first of beta here minus epsilon. What is beta? It's E prime. What is A is T. So hence, I found that follow of T includes first of E prime minus epsilon. Oh, that's one thing that I didn't say. Here in my set construction here, the superscript here is describing the symbols that I have had I've added into the set with each of these numbers I have here, which is each of these applications of the rules I have here. For example, using 1 here, I was able to put $ in follow of E. Then with follow of T here includes first of E prime. So number 2, I actually found that first of E prime is epsilon plus minus epsilon is plus. So I included plus into follow of T, such as my rule said here, my inference I found here. Then if I take the same rule number 2 on this rule here, E prime gives plus TE prime, where B is E prime, alpha is plus, A is T, and beta is E prime, then I know from this rule here, which is rule number 2 here, that follow of A includes first of beta minus epsilon. So follow of A, which is follow of T, includes first of beta, which is first of E prime. So follow of T includes first of E prime minus epsilon. So you see here that I found exactly the same fact. So it's going to happen quite often that you find actually the same fact. That you did not find something new here by applying rule number 2 using these 2 rules. Okay. Still, you have to do it consistently and find all the possible patterns in your rules. Then you can see that I can use this rule here and try to apply pattern number 2 here, where B is T, alpha is absent, A is F, and beta is T prime. So then follow of A, which is follow of F, includes first of T prime. Follow of F includes first of T prime. So follow of F includes first of T prime, which is minus epsilon, which is star. So follow of F includes star. Then finally, I come to this rule here, and I'm trying to apply this pattern here. So F gives E between parentheses, alpha is open parenthesis, beta is close parenthesis, A is E, and B is F. So follow of A, follow of E includes first of close parenthesis. First of close parenthesis is close parenthesis. So follow of E includes first includes close parenthesis. So follow of E includes first includes close parenthesis. Sorry. Then we see that I have tried to apply. I have found all the occurrences of pattern number 2 in my grammar. Then I go to find those patterns, occurrence of pattern number 3 in my grammar. Then pattern number 2, what I remind you is that what I'm trying to see is cases where certain non-terminal for which I'm trying to find the follow set can end an actual sentential form defining one of the right-hand sides. So for example, here, obviously E prime can finish this sentential form. So I have found an occurrence of this pattern where E prime is beta, A is T, and B is E. So following this rule here, I have found that follow of A, which is follow of T, includes follow of A, which is follow of T, includes follow of B or follow of E. So follow of T includes follow of E. Follow of T includes follow of E. So $ close parenthesis is included in follow of T. Then I can actually apply exactly the same pattern using the same rule because I know for a fact that E prime itself can evaluate to epsilon. So if E prime can evaluate to epsilon, then essentially T can end the sentential form here if E prime evaluates to epsilon. So then I have B is E, alpha is T, and A is E prime. So I found that follow of E prime includes follow of E. Follow of E prime includes follow of E. So then I basically add this to my set. Here is an interesting one. So here I can find this pattern here by having A or alpha is plus, A is T, beta is E prime, and B is E prime. So what I found here is that follow of E prime includes follow of E prime. Of course, this is not very interesting, but still, that's what this rule tells me. So if you finished parsing an E prime, then what can follow is anything that can follow an E prime, of course. And then you can actually find, or sorry, this was for this one here, sorry. The second one here. But here, if I actually use the same rule here, then I can find eventually that follow of T includes follow of E prime if E prime actually can evaluate to epsilon, which we know it can. Okay. So we're using this rule here. I find two different applications of the same pattern, which tells me both follow of E prime includes follow of E prime and follow of T includes follow of E prime. Then I can continue down the list of my rules and then apply to this pattern here, where B is T, alpha is absent, and A is F, and T prime is beta. So what I found here is that follow of F actually includes follow of F includes follow of T, because T prime can be absent here. So follow of T prime includes follow of T. However, if I apply this rule here, then I actually can find that follow of F includes follow of T if T prime can be nullified. And then similarly to what I found here, I can find that follow of t prime includes follow of t prime, and that follow of f includes follow of t prime, if t prime can evaluate to epsilon. Then I have found all these inclusion relationships. Now you see that these ones here, all they tell me is that there is an inclusion relationship between a follow and a follow. Now, if I apply these only in this particular order, it's possible that some of these actually will, depending on which order I apply them, then it's not going to get, if I applied them only once, then it's likely that it's not going to compute, do all the inclusions in the complete way. So if you would want to implement that, then you would need to actually reapply all of these here n times until in the last iteration, you have not actually added anything to any of the follow sets by the last iteration. So that's it. That's how you compute the follow sets. So you see that it's kind of a gymnastics here. So you don't, so you see that even for a simple grammar, it's quite the gymnastics. It's very easy to make mistakes, especially that you would have to reapply these rules over and over again and make sure that you have done all the inclusions in a complete manner. So you don't want to do this manually. So that's why using a tool is advocated, I might say. So let's talk a little bit more after we've seen that in more detail about recursive descent predictive parsing. I have explained quite a bit, I believe, clearly in the previous video. So you may want also to listen to the previous video to complement what I'm going to say here. So what is the method? So here we're talking about recursive descent predictive parsing. That's this parser that for each of the non-terminals in your grammar, you would actually hard code a function that implements the parsing of this non-terminal symbol. Yeah. So it's a hard-coded parser. Well, hard-coded, in it can be automatically generated. There are some parser generators that will actually generate automatically a recursive descent predictive parser. Now, what's the method? Well, first of all, as for any or the vast majority of parsing methods, you would need to compute the first and follow sets for every of the non-terminals that you have in your grammar. And for first sets, you also need the first set of the terminal symbols, which are themselves. So arguably, you don't need to compute them. So for each non-terminal, you have a function that you will implement, or member function or free function, depending on what programming language that you're talking about. In each function, for each possible right-hand side of the corresponding production, we have a possible path to follow. So essentially, for every function, there is a path in this function for each right-hand side defining the non-terminal for which this function is doing the parse. The choice, because you have to make a choice as to which of the branches you will choose, the choice is made according to the first set of the right-hand side in question. So if the next token in input is in the first set of the first right-hand side, then you make a decision to go in this branch and parse using this right-hand side. If it is not, then if it is in the, if the next token is in the first set of the second sentential form defining this non-terminal, the second one for the second rule, then you would choose the second rule, and so on and so forth. Okay. And if you have one of the alternatives, one of your rules, one of your right-hand sides for this non-terminal symbols definitions is epsilon, then you will have another path, but then you would choose to go in this path only if the next token in input is actually in the follow of the non-terminal in question, non-terminal that you're currently parsing. The idea, of course, being if this non-terminal is not there, then the next token, which should be, is what can follow this non-terminal. And if it's not, then it's not, you should not go in this branch. Okay. And then once you have all these paths that you branch upon all these conditions, if no valid path is found, then the function returns false. If any of the paths is followed without error, then the function returns true. And then as you're doing the parse, you're actually trying to match the tokens for any of the terminal symbols that you find in the sequence that you successfully parse in the sequence, or if you encounter non-terminals, then you would call the function that is doing the parse for this particular non-terminal. So how it would start, this is what I name here the parse function. That's the top function that is called when you want to do a parse. So what it does is, here you see this is next token function is the call to the lexical analyzer. Okay, so this next token function gives you the first token in the program when you start. And then you put that in a variable called look ahead. And then if you can parse the start symbol successfully and then match the end of the program after, then you return true. So essentially it says, if you can successfully parse a program and what you have after the valid program is the end of file, then you have successfully, that this program was successfully parsed. If you cannot parse the program with the starting symbol function, or that if you successfully parse the starting symbol and it is followed by something which is not the end of the program or the end of file, then you actually return false. Basically, this is not a valid program. So for example, if you have a valid program and then you have some more keywords after or tokens after, it's not a valid program. So that's how it all starts. And you see that this starts by calling this parsing function here. Then what is this match function? So what the match function receives a token. So that's basically the token that you pass to it here is a token that you are expecting. So this match function, it will take this token you're expecting and it will compare it with the look ahead. So you compare what you expect with what you have. If what you expect is what you have, then you say that what I had was successfully parsed, and then you continue to the next token. And if not, then you say, well, that was a parsing error. So if look ahead is the same as the token, then you go to the next token. Basically, you advance to the next token. You successfully parse this token, and you return true. If the look ahead is not the next token, then you advance, but then you say this was a parsing error. Okay. This token I have seen was a syntax error. Now, what's the, I would say, generic definition or form of a parsing function? So let's say you have in your grammar, you have rules of the form left-hand side gives right-hand side 1 or right-hand side 2 or epsilon. Okay, that's a generic definition of what is a rule that you might find, or a set of rules that define LHS or the non-terminal LHS in your grammar. Now here you essentially have all these alternatives here. For each of the alternatives, for each of the right-hand sides, you should have one branch. Okay. In this case, we have one branch for right-hand side 1, one branch for right-hand side 2, and then so on and so forth, and then one branch finally for the epsilon rule. Okay. So you see that the condition for you to branch on one of these here is you check if the look-ahead symbol is in the first of this right-hand side. Again, same thing. If you have any right-hand side that is not epsilon, then you would branch to this branch if the look-ahead symbol is in the first of the right-hand side in question. And then finally, if you have an epsilon rule, then you would branch to this branch only if the look-ahead symbol is in the follow of the left-hand side. Okay. So it's first of right-hand side, or if there's an epsilon rule, follow of left-hand side. Then once you branch to any of these that are not epsilon, then what you do is you actually match all the you call the functions, you call the parsing functions, because you have a sequence of symbols in this right-hand side. For any of the non-terminal symbols, you would call the parsing function for this particular symbol, this particular non-terminal symbol. If you find in the sequence terminal symbols, then you would actually match this terminal. Okay. Then if you successfully call all these functions, they all return true, and eventually all the matches return true, then you have successfully parsed using this particular right-hand side in recognizing something which is an LHS. Then here what I say is that I've successfully applied this rule, and that's what I would print, for example, on the console, something. And then I would return true. And I do this for every, so exactly the same form for every of my right-hand sides that are not epsilon. If I have an epsilon rule, then essentially I check if the look-ahead symbol is in the follow of the left-hand side. If it is, then, so what is it that you do when you go ahead in the sentential form that defines this right-hand side? Well, there's no sentential form, so automatically it applies without any further steps. So you successfully, if look-ahead is in follow of left-hand side, then you successfully have found an application of this rule here, and you return true. If none of these branches can be branched upon, then this was a syntax error. Okay. And you basically bail out of the parsing of this left-hand side. Okay, so that's the form for every of your functions in your recursive descent predictive parser. Then, okay, so let's do it I'm going to go quickly over this because it's quite self-explanatory. So I actually do one function for every of my right-hand sides, left-hand sides, or non-terminal symbols. So I do it for E. E is TE prime. There's only one right-hand side, so there's only one branch. So if I parse an E, if a look-ahead is in first of TE prime, then I parse a T, I parse a TE prime, I parse an E prime. If both of these return true, then I have successfully applied this rule, I return true. If any of these returns false, then I return false. If this branch here cannot be branched upon, then this was a parsing error. So you see that this results in a parsing error if the next token is not in the first of this, but also returns a parsing error if T or E prime actually resulted in a parsing error. Then let's do this for E prime. So here I see I have two branches. So I have one branch for the plus DE prime And because I have an epsilon here, I have a branch, an epsilon branch, you might say, which is using follow of E prime. So this is using first of T plus TE prime, and this is using follow of E prime. So when I start parsing an E prime, if my look ahead is in first of plus TE prime, essentially if it's plus, then I match plus. Of course, here this is going to match. The match is going to be successful because I already know that the next token is plus. Okay. This one is going to be kind of for free here in this particular rule. Then if I match the plus, which I will, then I should call the function for t and then the function for e prime. If all of these return true, I have successfully used this rule and I return true. If any of these return false, then I return false. If this branch is not followed upon, or if the next token is not plus, then I check if the next token is in follow of E prime. If it is, then that would be indicative that I'm using the rule found in application of the rule E prime gives epsilon. And then I automatically return true. If none of these branches is possible, then I found a syntax error. So for t, I only have t gives ft prime. So it's very similar to e gives te prime in form here, except that here I'm checking if look ahead is in the first of ft prime. If it is, then I parse an f, parse a t prime. If both of these return true, I successfully applied this rule, then I return true. If at least one of them returns false, then I return false. There's only one branch, so if this branch does not work, this is a syntax error. T prime in form is very similar to E prime. So I have star FT prime. So here I check if the look ahead is in first of star FT prime, which is star. If it is, then I match star, which will, if I branch here. And then I parse an F and then parse a T prime. If all of these return true, I've applied this rule, return true. If any of these returns false, I returns false. Then if this branch is not possible, then I check if this branch is possible here by checking if the next token is in follow of T prime. If it is, then I'm using I've successfully found a use of this rule. So one thing I didn't say is that if you don't have an epsilon rule, then you should not have this branch here. Okay? This branch should be there only if you have epsilon rules. If you put it there, if you don't have epsilon rules, it's gonna, the parsing is gonna be wrong. The F is particular in that it has multiple branches and they all start with a terminal symbol. So, and you don't have an epsilon rule. So first branch is if the next token is first of 0, which is 0, then I match 0, which would be automatic because that's what I was expecting and that's what I match. So I've successfully applied the rule F gives 0, return true. If this is false, then I return false, but we clearly see that it's not possible. Okay, so why would I write that? Just to make sure that all the functions are written exactly the same way. Okay, of course, if I would want to optimize my compiler, I might actually omit this here, which will, it's basically, this is dead code here that would not ever be executed. But anyway, in order to have the same form for all of my functions, I make them all the same. And same thing or similar thing for the second branch, which is this one here. So if my look ahead is in first of 1, then I match 1, and I say successfully applied F gives 1, return true. If not, return false. Which would be impossible, but let's keep it for the form. And then if not, then if the lookahead symbol is in the first of E between parentheses, which is open parenthesis, then I match open parenthesis, then call E, which would make me go back to the top again and parse an E that happens to be between the parentheses, and do this all over again. And then once I've successfully parsed this E, then I should have the matched close parenthesis. So then I've successfully parsed an E between parentheses, and I return true. If any of these does not match, for example, if I have open parenthesis that successfully parse an E and there's no matching close parenthesis, essentially here I would have a mismatched parenthesis, a syntactical error. Okay, so that's how you do the recursive descent predictive parser. Now, again, here it's kind of a simple example. The grammar is quite simple, few rules, few non-terminal symbols, and then a few right-hand sides, okay? And as well, the right-hand sides in this example are quite small. So the longer is the right-hand side, the more it creates more elaborated, trace of the whole parsing. That's one of the things. When you will do this assignment number 2, inevitably you're gonna have your parser is gonna end up being wrong in some way. And then you will have to trace the execution of your parser. That's one of the reasons why some people prefer to have this recursive descent predictive parser, because if you trace the execution of the program, you look at the code and you see what it should be doing by looking at the code. Okay. Then you look at your grammar rules, you look at the code. If you did it as I explained here, it's pretty clear what is the correspondence between your function and the actual rules in your grammar. Okay. So it's somehow easy to trace and figure out. Okay. It's intuitive. When you look at the code, there's correspondence between the code and your grammar. That's one, I would say that's the main reason why people want to do that in this assignment. Traceability of the parser. Now you can do actually exactly the same process, but using what is called a table-driven predictive parser. Now what's the method here? First, you compute the first and follow sets. Again, any parser you build, you will have to, it starts with that. It's the first step. Then you build the parser table. So there's an algorithmic definition or a formal definition that allows you to actually take the rules of your grammar, the first and follow sets, and actually transform these rules of the grammar and the first and follow sets into a parsing table. Okay, so that's what I'm going to show right away. Then once you have this table, then the only thing you need to have is the parsing algorithm, which is always the same. So independently of what grammar you are parsing, this algorithm will always be the same. If you change the grammar, you don't have to change the algorithm. What you need to change if you change the grammar is to reconstruct the table. Okay, so that's what some people like. That if something is wrong with your parser, you don't change code, you just change what's in the table. Okay. Of course, that assumes that you have some kind of tool that can generate the table, or that you have some very good intuition as to what's the process of creating the table to figure out what's should be in the table. Much better idea if you have a tool that enables you to automatically generate the table and that you don't do it manually. Nevertheless, I'm going to show here what's the concept involved in building this table, which is this algorithm or formal definition here. So it's kind of similar to the concept we had before when we explained what is the rules, the inference rules for determining inclusion relationships between follow set and either other follow sets or first sets. Okay, so it's kind of the same idea. You're looking at the rules of your grammar. You're trying to find some patterns. Once you find a pattern, it tells you that you can infer something from the presence of this pattern. In this case, you would infer that there are some entries that should be put in this inside of the table. So so essentially you do, how it goes is that you take every rule inside of your grammar. Okay. So once you isolate one rule, one very specific rule with one, left-hand side, right-hand side. Basically, if you have a rule, A gives alpha, then you do step 2 and 3. So basically, you take every rule, and then you try to see if pattern number 2 or rule number 2 applies. If it does, then you apply, you find certain inference, which leads you to insert some entries in your table. And for rule number 3, you check if a certain pattern applies. If it does, then it would lead you to enter other kinds of entries in the table. Okay. And you do this for every of your rule in your grammar. Then essentially rule number 4, that's the easy part. Rule number 4 says, after you will have scanned over all of your rules in your grammar, trying to see if pattern 2 or pattern 3 applies, once you've expanded all the rules of your grammar, then you go back to the table, and any entry that is empty, that has not been filled by the execution of the preceding steps, any of the empty entries represents a syntax error. Okay, so of course, then number 4 here is the easy part at the end. Now, in this notation here, I'm using TT here. So essentially, TT is a parsing table. So the parsing table is a table for which you have for each, so it's a two-dimensional table. There is one row in this table for every non-terminal in your grammar. And there's one column in this table for every terminal symbol or token in your language. But you see that it can end up being quite a large table. You can have dozens of tokens and also dozens of non-terminal symbols. So that's why it's better, of course, if you do that professionally, that you use a tool to actually generate the table that would implement this formal definition here. So let's see how it goes. So eventually what I want to achieve is I have these rules, and I have my rules of my grammar, and then I had these transformation rules here. So I'm going to use these transformation rules in my grammar or to my grammar. We'll apply these transformation rules to my grammar, and then I will find the top-down parsing table that corresponds to this grammar. Okay, you see that there's one row for each of my non-terminal symbols, and I have one column for every of the terminal symbols. Essentially, this table presents the fact that if I'm starting to parse an E and I see 0, then it says I should apply rule number 1. If I'm parsing an E and then I see a 1, the next token is 1, I apply rule number 1. If I'm parsing a T prime and I see closed parenthesis, I'm applying rule number 6. So I have identified, of course, my rules here by R1 to R9. If I'm parsing an E prime and I see 0, this is a parsing error. Okay, that's what this table means. We'll see the parsing algorithm after we figure out the example of how to build a table. Okay, so this procedure here says for each of the rules in your grammar of the form A gives alpha. So start with, basically go from rule 1 to rule 9. in this particular order. It doesn't matter in what order I'm actually covering all the rules. So here I have two possible rules to apply. Okay, so depending on what is in first of alpha, which is first of my right-hand side. So first of my right-hand side, alpha here is first of TE prime. So first of TE prime is 0, 1 open parenthesis. So first of T is 0, 1 open parenthesis. Okay. Of course, if, yeah, so first of TE prime is 0, 1 open parenthesis. Then if, of course, if T would maybe evaluate to epsilon, which it does not, then I would also include first of E prime in this set here. Okay, but this does not happen in our grammar. You have to look out for that, but in this particular example, it does not ever happen. So first of TE prime is 0 and 1 open parenthesis. So this rule says if that's the case, then you add inside of the table the entries at the coordinates A for each T in first of alpha, or 0, 1 open parenthesis, and you add these entries in the table. So basically, I add to the table TT of E0, TT of E1, and TT of open parenthesis, where, of course, E is my non-terminal that I'm currently processing for this particular rule. So TE0, TE1, T open parenthesis. So for E, so I put R1 in TE0, TE1, and TE open parenthesis. So R1 is in E0, E1, and E open parenthesis. So that's it for this rule. And also for rule number 3, which might apply, but in this case does not. So rule number 3 said that if first of alpha or first of TE prime includes epsilon, so basically meaning that is the TE prime here can evaluate to epsilon, both of them can evaluate to epsilon. If it would, then I would add in my table an entry at coordinates A and T, where T are the elements of follow of A, this application of this rule. Okay. So that would be the case where if an E using this rule can evaluate to epsilon, then what I want to do is to somehow branch to what follows a T, what follows an E. Okay. But in this case, that does not apply because T E prime cannot both evaluate to epsilon. Then I'm doing rule number 2. So E prime gives plus TE prime. So using rule number 2 here, I actually find the first set of plus TE prime, which is of course plus. So that means in the table, I include at coordinates E prime plus, I include rule number 2. So E prime plus rule number 2. Then this rule does not apply to actually, the rule number 3 does not apply to this rule here. Then here I have E prime gives epsilon. So here epsilon does not have a first set. So I apply rule number 3. So rule number 3 is, I remind you, if the right-hand side can all evaluate to epsilon, it's epsilon itself. So obviously that's the case. So that tells me follow of E prime is, in this case, I found that I used the fact that follow of E prime is $, close parenthesis. So this rule here tells me that I should add in the coordinates of the table E prime and the follow of E prime. the rule number 3. So TT of E prime $, and TT of E prime close parenthesis is rule number 3. E prime close parenthesis and $, is rule number 3. Then I go to rule T gives FT prime. So first of FT prime is first of F, which is 0, 1 close parenthesis. And as F cannot evaluate to epsilon, then that's where it stops. So that's basically using rule number 2 tells me that I should add to the table at coordinates T and the first set of F T prime, that's TT of T0, T1, T open parenthesis, I will add rule number 4. T0, 1 open parenthesis, rule number 4. These 3 entries here have been added. Then go to the next rule, and then I repeat, because F and T prime cannot both evaluate to epsilon in sequence, then I don't have an application of 3. Then I go T prime gives star FT prime, which was my rule number 5. So here I compute first of star FT prime, which is obviously star. So then I found using rule number 2 that T prime in the table, I have at coordinates T prime star, I have rule number 5. T prime star, rule number 5. Star FT prime cannot all evaluate to epsilon, so I don't have an occurrence of rule number 3 for this rule. Then I have T prime gives epsilon, which is, of course, all the right-hand side it can evaluate to epsilon because it's epsilon itself. So what I'm finding here is that I must use the follow of T prime, as this rule says. Follow of T prime is plus $ close parenthesis. So it tells me at the table at coordinates T prime and plus $ close parenthesis, I have rule number 6. So T prime close parenthesis plus and $, I have rule number 6. Okay. Then that's some of the easy cases here. So I have if F gives 0. So first of alpha, which is my right-hand side, first of 0 is obviously 0. So in TT of F0, I put rule number 7. TT of F0, rule number 7. Exactly the same thing, but for rule number 8, first of 1 is 1. So TT of F1 is rule number 8. TT of F1 is rule number 8. Then F gives E between parentheses. First of E between parentheses is open parenthesis. But coordinates T, F, open parenthesis, I have rule number 9. TT of F, open parenthesis, rule number 9. Okay. Thus, I have covered all my rules. Then I have actually constructed all my table. Of course, then I would need to do this step here, by which case, basically, I'm assuming that I actually found by this rule that every of the empty cells in my table are syntax errors. We will come back to that in the next lecture when we cover error recovery. Okay. So this is how I can take this set of rules, grammar rules, and then use these definitions to infer a parsing table, a top-down predictive parsing table for this that corresponds to this grammar. So you see that it's quite involved here. And this is, again, a very simple example. It's quite the gymnastics in order to do it without making some mistakes. You can imagine that the more rules that you have, the bigger are every of your right-hand sides. The more rules you have, more alternatives you have, the more this process is complicated. So you want to do this somehow automatically. doing it by hand, you're just asking for trouble and making it, if you fill the table by hand, you will inevitably make some mistakes, and it's going to be a problem to figure out where or when, or did you not make some mistakes, of course. Now, what we need is to actually implement or find out what is the parsing algorithm. Parsing algorithm, what it does is that it receives the next token and input, it has the table, and then it sees the next token and input, and then depending on what is shown in the table, what is in the table will make a decision as to what rule to apply. Now, what comes with that is that it must actually remember what sequence of non-terminals it is actually parsing at this point. So it actually uses a stack to store the symbols that it had started to actually compute, okay? So that it remember what is the sequence that it is currently in, so that it can actually store this sequence in the stack. And then you would add things to the stack as you start parsing a right-hand side. And then once you, and then you would do substitutions in the stack as you use more rules to parse right-hand side. So your stack is growing. And as you successfully parse a right-hand side, then you would remove the symbols that represent this right-hand side from your stack. So your stack is going to grow, and shrink until at the end, what you have is actually only the starting symbol. So you start with the starting symbol and you want to end with the starting symbol. Okay, so just abstractly speaking here, it's going to be probably more up in the air here when I give this description, but we'll see with an example right away. And you'll see that it's not very complicated. So if somebody wants to use this method here, you have to know by heart how it's actually happening. Okay. Because if you want to trace your parser after, you're going to have to be totally aware of what's the operation here. So you see that I have a push, and I also have what is called inverse right-hand side multiple push. Okay. So you're pushing symbols on the stack. So either terminal or non-terminal symbols. Okay. So essentially here I start by pushing the end of the program, because after the end of the program, what I want to have is the end of the program. So I'm pushing the end of the program on the stack, and then I'm pushing the starting symbol on the stack. The idea here is that as I push the starting symbol on the stack, I'm going to do a derivation step to actually transform this starting symbol into something else. So I'm going to basically build my derivation by doing derivation steps that are transforming symbols into sentential forms. Okay, so I'm going to also show that very easily here. You can see that you're actually doing a derivation. That's one of the things that's included in the table here. So you have every parsing step is actually representing a derivation step. Okay, so you're pushing the end of the program on the stack, and what you evidently want is after, when you come at the end, that what you should have after you successfully parse the S, what you want to have is that on the stack should be this $ that you put in the beginning. Okay. So that S would have been transformed in different steps into a large sentential form, and that eventually it's going to reduce itself, and that at the end, what you want is to have, again, the $ on top of the stack. Of course, you are getting the next token from your lexical analyzer, which is represented by this A variable. Then you have this forever loop here that loops until the top of the stack is different from $. So you want to stop only when you have $ on top of the stack. And you, of course, stop either if you have $sign on top of the stack or if you see a parsing error. Here, I'm not going to explain what happens if you see an error. That's going to be in the next video. So here, essentially, top is, of course, my top of the stack, and I identified this with the variable x. Then there are two possibilities here once you are here. So if x, or the top of the stack is a terminal, then what you do is you check if x, the top of the stack, is the next token. If so, then you pop this x from the top of the stack and you go to the next token. Now, this is where it's important to see the relationship between this algorithm and what we were doing in the recursive descent predictive parser. If you remember the match function in the recursive descent predictive parser, that's exactly what it was doing. It was saying, I'm expecting a certain token. If this token is what I have in input, then I go past this token and I say, I've successfully parsed this token. This is exactly the same concept as the match function here. Okay. If it is the same token, you pop the stack and you go to the next token. If not, then this is a syntax error. If it is not a terminal symbol on top of the stack, then it must be if it's not a terminal on top of the stack, it must be a non-terminal, because this is the only two things we're pushing on the stack. Then this is where you would actually peek into the table to know what rule or what right-hand side you would actually start using to expand this non-terminal. To substitute the occurrence of this non-terminal in the sentential form by one of its defining right-hand sides. That's essentially what you're doing here. So you're going to replace this non-terminal that is now on the stack. You're going to replace it by its right-hand side. Because it is a stack, it's basically last in, first out, then you have to push the symbols in the right-hand side in reverse order. That's essentially what this is saying here. So you peek into the table at coordinates x, which is top of the stack, and then a, which is the next token. If it is not an error, then you remove this non-terminal from the stack and you replace it by its right-hand side, the right-hand side of the rule that you will find in the table. So if you peek at a certain point in time, let's say, for example, here I have t on top of the stack and I have 0. I gotta go to the table t0 to find R4. R4 is this here. So I'm gonna pop the t from the stack and I'm gonna replace this t by t prime f. So I pop the t and replace it by t prime f. So I've essentially done a substitution. I have done here one derivation step in the proof that proves that this program is valid according to the grammar. So you see, that's what I have here. Okay, we'll see that later. So if I find an entry in the table, then I essentially pop this non-terminal from the stack, and then I replace it by the right-hand side in reverse order of this particular rule that I found in the table. So you see that this table is telling me in every possible context, if I find a rule inside of the table, I just replace the non-terminal in question by the right-hand side of the rule I found in the table. If I don't find something or a rule in the table, then that would be a syntax error, as we saw earlier. And then once I'm finished this, then once I'm going out of the loop, then if I don't find on top of the stack the $sign and or error is equal to true, then I return false, saying that the parse was unsuccessful. If I have on top of the stack $sign and then I have a successful parse. So then let's go with the example. So here I have my stack for my parser, my table-driven top-down parser. This is the input stream of tokens that I have. This is the productions that I will eventually identify as a result of my parsing steps. And then every time I apply a production, there's going to be a derivation step. For example, here, I am actually transform this E into TE prime. So here I have a derivation step that transforms the sententional form E into TE prime. Here I'm transforming a T into FT prime. So I'm transforming this T into FT prime, which is followed by E prime. Okay. So you see that's one is pretty clear what's the derivation steps that are involved. Okay. Now let's do the whole example. So first I have E. So I start by pushing $sign and S on my top of the stack. So I push $sign and my S, my starting symbol, is E. So $sign E. Then I go inside of the while loop, and what I have is a non-terminal symbol on top of the stack. So essentially I'm going to this branch here because the first branch is for terminal symbols on top of the stack. So here I go here, so it prompts me to go to the table at coordinates XA. So this is X and this is A. So E open parenthesis is R1. R1 is transform E into TE prime. Well, if you remember what is happening here, I'm going to actually pop the E from the top of the stack, and I'm going to take the right-hand side of this rule and push it in reverse order on my stack. So I'm going to pop this E from the stack. It's now not on the stack anymore. And what is the right-hand side of this rule? That was E open parenthesis. That was rule number 1. So the right-hand side of this rule is TE prime. So I'm pushing E prime and pushing T. So I pop the E from the stack and push E prime T. Then I go another iteration. And now I have T on top of the stack. I'm not going to go back to the slide. You'll see that it's quickly becoming natural once you figure out what it's actually doing. So I have T open parenthesis. So I have a non-terminal here. So I peek into the table T open parenthesis. T open parenthesis rule number 4. So I transform this T into an FT prime. So I pop my T from the stack and I replace it in reverse order, push in reverse order FT prime. So I push T prime F. So I replace T by T prime F. So I replace this so this is the derivation steps. The derivation steps that's happening here. So the T has been replaced by FT prime. Okay. Then I have F on top of the stack. So that's a non-terminal. So I go F open parenthesis. F open parenthesis is this one here. Sorry, I have to move this here. Okay, so F open parenthesis, rule 9. Rule 9 is F gives E between parentheses. So I transform, I remove this F here, and I replace it by E between parentheses in reverse order. So I've transformed this F into an E between parentheses, applying this rule here. Now I have open parentheses on top of the stack, which is a terminal symbol. So that's why here I'm going to go to this branch here, which is popping, checking if the next token is equal to what I have on top of the stack. If it is, then I pop and go to the next token. So it is the same, open parenthesis, open parenthesis. So I pop this from the stack and I go to the next token. So you see that here I'm at 0 and then the parenthesis has been removed. Then next step, another iteration, E0. E0 is R1. R1 is, sorry, this is in the way, I'm going to push it here. So E0 is R1. R1 is replace E by TE prime. So I pop E from the stack and replace it by E prime T, which is the right-hand side in reverse order. And then I do this derivation step here. Now I have next iteration T0. T0 is rule 4. Replace T by Ft prime. So I take this T, pop it from the stack, and replace it by T prime F. Next, and then I have another derivation step. F0, next iteration, rule 7. Rule 7 is F gives 0. So in this case, I pop the F and I replace it by 0. Then next iteration, I have a terminal symbol here. So I check if this is the same as this. Yes, it is. So I pop this from the stack and I go to the next token. And I'm left with T prime plus. T prime plus is rule 6. Rule 6 is T prime gives epsilon. So that's my epsilon rule. So I'm actually popping T prime from the stack and I'm replacing it by nothing. So I basically applied the epsilon rule on T prime. Now I have E prime plus. E prime plus, rule number 2. Rule number 2 is E prime gives plus TE prime. So then I'm going to replace this E prime by E prime plus T. Then I have plus, which is a match. So then I pop this plus and I go to the next token. So the next slide here for the continuation. Now I have T and 1. T1 is rule number 4. Replace T by Ft prime. Pop the T, replace it by T prime F. And I have F1. Again, the derivation steps are being done here. And the rules I have applied to do this transformation step. Or the derivation step. So F1 is rule number 8. Replace F by 1. Pop the F, push the 1. 1, 1 as a match. So I pop this and I go to the next token. Then I have T prime close parenthesis, T prime close parenthesis, rule number 6. T prime is epsilon. T prime is pop, replaced by nothing. E prime close parenthesis, E prime close parenthesis, rule number 3. E prime is epsilon. Pop the E prime, replace it by nothing. Close parenthesis, that's a match. Pop the close parenthesis, go to the next token. T prime star, T prime star is rule number 5. Rule number 5 is T prime gives star Ft prime. So I remove the T prime and replace it by T prime F star. Then I have star star, pop the star, go to the next token. F0. F is replaced by, F0 is rule 7. Rule 7 is replace F by 0. Then, so I pop the F and then push 0. Then I have 0, 0. This is a match, so pop 0, go to the next token. Then you see what's happening here, what's coming. T prime $, T prime $, is rule 6. Nullify the T prime. So T prime is popped and is replaced by nothing. And I have E prime $. E prime $, is rule 3. Nullify E prime. E prime is popped, replaced by nothing. Then what I have on top of my stack is $, which is my ending condition of my while loop. And then what I have is $, on top of my stack. Nothing gave me false anywhere. So basically I have a parsing success. Okay. You see, this one is much more, I would say, for those of you that like things that are systematic, this is much more systematic, I might say. However, the point is that if you're understanding, or if you want to trace your parser by your knowledge of what are the rules, then you see that the parser is not using the rules really. The parser, what it's using is the parsing table, which is some kind of encoding of the rules. Okay. So it is more, I would say, abstract, and it's more kind of cryptic to actually trace this parser. If something goes wrong, something is wrong with your parsing process, it's going to be more abstract to actually trace it, because as you're tracing, it's not using the rules, it's actually rather using the content of the table, which is some kind of abstraction of your grammar. Okay. So yes, there are some advantages to this. So depending on how you like things, when you write your programs, you might like this. Some other people would prefer to see their own code in order to trace what is really happening. Okay. One clear advantage of this one is that if something is wrong with your parsing process, then clearly the only code you need to change is the content of the table. You don't have to debug anything. It's just clearly that's the table that is wrong if you have something wrong with your parser, unless you implement the algorithm wrong. But once the algorithm is proven to be correct, then if you have parsing errors, if the parser does not behave how it should, then clearly the only thing that can be wrong is the table. And if you have an automated way to generate the table, then that can be avoided. So that's it for this lecture.